This is now the part 18 of the LEED V4 Reference Guide for Homes Design and Construction online review. Again, all the pictures or images in this video are from Google and USGBC website. If you have comments, suggestions or complaints regarding the images, pictures or in this video, please email me at nelca_roco@yahoo.com, and I will immediately reply to you and take action on whatever the reason of your email. Thank you. Why I created this online reviewer. To help myself and others to pass the LEED AP exam in one shot. These are the LEED credit categories. On my previous video, we discussed the Water Efficiency Credit 3, Outdoor Water Use. Now we will proceed to the first prerequisite of Energy and Atmosphere, the Minimum Energy Performance.
Energy and Atmosphere Overview. The Energy and Atmosphere, EA, category approaches energy from a holistic perspective, addressing energy use reduction, energy-efficient design strategies, and renewable energy sources. The current worldwide mix of energy resources is weighted heavily toward oil, coal, and natural gas. In addition to emitting greenhouse gases, these resources are non-renewable, their quantities are limited or they cannot be replaced as fast as they are consumed too. Though estimates regarding the remaining quantity of these resources vary, it is clear that the current reliance on non-renewable energy sources is not sustainable and involves increasingly destructive extraction processes, uncertain supplies, escalating market prices, and national security vulnerability. Accounting for approximately 40% of the total energy used today, 3 buildings are significant contributors to these problems. Energy efficiency in a green building starts with a focus on design that reduces overall energy needs, such as building orientation and glazing selection, and the choice of climate-appropriate building materials. Strategies such as passive heating and cooling, natural ventilation, and high-efficiency HVAC systems partnered with smart controls further reduce a building's energy use. The generation of renewable energy on the project site or the purchase of green power allows portions of the remaining energy consumption to be met with non-fossil fuel energy, lowering the demand for traditional sources. The commissioning process is critical to ensuring high-performing buildings. Early involvement of a commissioning authority helps prevent long-term maintenance issues and wasted energy by verifying that the design meets the owner's project requirements and functions as intended. In an operationally effective and efficient building, the staff understands what systems are installed and how they function. Staff must have training and be receptive to learning new methods for optimizing system performance so that efficient design is carried through to efficient performance. The EA category recognizes that the reduction of fossil fuel use extends far beyond the walls of the building. Projects can contribute to increasing the electricity grid's efficiency by enrolling in a demand response program. Demand response allows utilities to call on buildings to decrease their electricity use during peak times, reducing the strain on the grid and the need to operate more power plants, thus potentially avoiding the costs of constructing new plants. Similarly, on-site renewable energy not only moves the market away from dependence on fossil fuels but may also be a dependable local electricity source that avoids transmission losses and strain on the grid. The American Physical Society has found that if current and emerging cost-effective energy efficiency measures are employed in new buildings and in existing buildings as their heating, cooling, lighting, and other equipment is replaced, the growth in energy demand from the building sector could fall from a projected 30% increase to zero between now and 2030. The EA section supports the goal of reduced energy demand through credits related to reducing usage, designing for efficiency, and supplementing the energy supply with renewables. 1.org web link. 2cnx.org web link. 3unep.org web link.
Energy and Atmosphere has performance and prescriptive path, or a combination of both paths. Minimum energy performance is the first prerequisite of EA category. It is required. Energy and Atmosphere Prerequisite 1. Minimum energy performance. Intent. to improve the building's overall energy performance and reduce its greenhouse gas emissions. It is prerequisite or required. Requirements. Meet all of the following requirements. 1. Meet the requirements of Energy Star for Homes, version 3. Complete the thermal enclosure system radar checklist, defect system quality, installation radar and contractor checklists, and the water management system. Builder checklist. Certified passive house projects automatically meet the thermal enclosure system radar checklist requirement. Achieve a HERS index rating at or below the HERS index target, or USGBC approved equivalent for projects outside the US, or meet the requirements of the Energy Star for Homes version 3 prescriptive pathway, which includes meeting or exceeding all components of the Energy Star reference design. 2. At least one of the following appliances must be Energy Star qualified, or performance equivalent for projects outside the US, and installed in each dwelling unit. Refrigerator, dishwasher, or clothes washer. 3. All duct runs must be fully ducted, that is, building cavities may not be used as ducts. Existing portions of an existing building are given the following allowances. Thermal enclosure system radar checklist. 2.1. Slab insulation is strongly encouraged but not required to meet or exceed 2009 IECC levels. 4.1. Attic insulation at the intersection of existing roof and existing exterior walls does not have to meet R value requirements. 4.4.5e. Advanced framing is not required on existing framed walls. 5.2.1. Existing sill plates on top of concrete are not required to be placed on a foam gasket. Water managed site and foundation. 1.3. A capillary break under an existing slab is not required unless there are visible signs of moisture damage on the slab floor. 1.5. Exterior below-grade walls are not required to be damp-proofed on the exterior surface unless there are visible signs of moisture damage on the interior of the wall. 1.8. Drain tiles surrounded with clean gravel and fabric filter are not required for existing slabs, unless there are visible signs of moisture damage on the slab floor. 2.3. Water managed wall and roof assembly requirements are not required for existing walls or roofing unless there are signs of moisture damage related to vulnerabilities in the walls or roof. Prerequisites required for all projects, whether they use the EA Performance or EA Prescriptive path. Energy and Atmosphere has the highest credit requirements. It has Performance and Prescriptive path. The maximum possible points to be earned is 38 points. Important note, a minimum of 8 points must be achieved in the combined LT and DIA sections.
Behind the intent. Homes new construction. Energy performance is the foundation of any green building. In LEED B, D and C, homes, a new home must meet the minimum performance levels of Energy Star for Homes, version 3. Energy Star is an EPA program that takes a whole building approach and provides a benchmark for energy efficiency, comfort, and durability. In addition, Energy Star addresses most of the common failures in residential construction. Homes existing buildings. LEED B, D and C, homes may be applied to existing homes undergoing significant renovations. Energy Star for Homes, however, is primarily a new construction program and not always applicable to existing structures. Therefore, existing homes projects seeking LEED certification are exempt from Energy Star requirements for foundations, slab insulation, foundation damp proofing, capillary break at foundation sill, and foundation drainage, alterations to existing structural wall, attic, and roof framing, and roof water management. The exception is when there are visible signs of moisture damage on the wall or roof, in which case the moisture problem must be addressed in accordance with Energy Star standards. Multifamily midrise. An optimized building design can substantially reduce energy use, often for a modest initial cost with a short payback period, when it includes load reduction, improved mechanical system efficiency, and smart operational strategies. An integrated building design can lower operating and maintenance costs and improve indoor air quality, thermal comfort, and access to daylight. Partnering with the design team, qualified energy modelers can interpret the results of these complicated analyses to maximize the benefits to the project. When initiated early in the design process, an energy simulation serves as a design tool instead of a compliance check. One of the greatest benefits of early energy modeling is better integration of interrelated design issues, which encourages dialogue about assumptions concerning building components and systems. Information on energy use and costs thereby plays a bigger role as design decisions are made. ASHRAE 90.1/2010 was chosen as the standard on which to base the requirements because it continues to push building design toward greater energy efficiency. Specifically, a study by the U.S. Department of Energy showed an average improvement of 18% across all building types when ASHRAE 90.1/2010 was applied instead of ASHRAE 90.1/2007. A structure must not just be designed for energy efficiency, the achievement must be verified through commissioning. For this prerequisite, the modeled building energy cost savings must show a minimum 5% improvement over baseline building performance, as defined by ASHRAE 90.1/2010. Diagnostic tests and inspections are then performed using the ENERGY STAR multifamily high-rise programs testing and verification protocols, version 1.0, or the USGBC process outlined in the requirements for this prerequisite. Commissioning ensures that the building has been constructed as designed.
Step-by-step guidance for homes. Step 1. Assemble team. As early as possible, assemble experienced design and verification teams, including a home energy rating system, HERS, rater or other USGBC approved energy rater. Many green raters are HERS raters. The HERS rater creates an energy model that rates the home's performance. In addition to its function as documentation, the HERS rating process is a valuable tool in designing the home. Options for improving the efficiency of the home can be modeled and the corresponding energy savings can be used to make design decisions. ENERGY STAR certification affects nearly every construction trade. The contractor installing the foundation must properly address moisture and thermal issues. Likewise, the plumber is involved with different types of efficient plumbing equipment and hot water piping designs. Developing an ENERGY STAR and LEED training program for trade contractors is a good strategy for success. Step 2. Choose compliance path. Homes may earn the ENERGY STAR label using either a prescriptive path or a performance path. Although projects may pursue either one, the performance path is strongly encouraged because of the value that energy modeling provides in helping project teams make informed decisions. See further explanation, performance path, and further explanation, prescriptive path. The performance path provides flexibility to select a custom combination of measures so that the home equals or betters the minimum performance of the ENERGY STAR reference home. Equivalent performance is assessed through energy modeling. Using a home energy rating software program approved by the Residential Energy Services Network, RESNET, a HERS rater models the rated home and verifies that the resulting HERS index meets or exceeds the ENERGY STAR target. The prescriptive path provides a single set of measures that can be used to construct an ENERGY STAR certified home. Step 3. Decide on specific compliance measures. For the performance path, have the energy model completed by a qualified HERS rater. Energy modeling may be used to perform cost-benefit analysis of different energy upgrades and design features, such as window overhangs or home size. The cost-benefit analysis can be performed in conjunction with a design charrette to facilitate integrated design. See Integrative Process Credit. For the performance path, a builder may selectively upgrade certain aspects of the home while installing other items at code minimum levels, effectively making trade-offs. For example, a builder may upgrade the windows because the supplier offers very competitive pricing, but maintain wall insulation levels at the code minimum because there is a significant cost to upgrade in the local market. Which features of the home are upgraded does not matter, provided the home's overall energy performance meets the threshold. For the prescriptive path, ensure that all requirements will be met, such as the insulation levels, window performance, and heating and cooling efficiencies. Step 4. Design HVAC system. A qualified party should design the HVAC system, following manuals J, D, and S, to ensure proper sizing of equipment and the distribution system. Step 5. Inspect foundation. During the early phases of construction, the builder or a builder-assigned party must complete the foundation inspection elements of the water management checklist. Step 6. Complete pre-drywall inspection. The HERS rater must complete the thermal enclosure inspection after the insulation and air sealing are installed, but before drywall installation. Multifamily buildings may require multiple pre-drywall inspections, depending on how fire barriers are installed. A duct leakage test and envelope leakage tests are encouraged at this time because corrections may be more easily made before the installation of drywall. Step 7. Complete HVAC checklist. After system install, the HVAC contractor will start up the system and complete the HVAC contractor checklist. Step 8. Complete final inspection and tests. After construction is complete, the HERS rater must complete any final inspections and diagnostic tests, including verifying select measures from the HVAC startup checklist. Step-by-step guidance. For multifamily midrise. Step 1. Assemble team. The builder or developer should identify the project team that will plan, design, and build the home. The team should include professionals with both knowledge and experience in all LEED credit categories. These professionals work together to develop the project goals, identify potential challenges, and determine how best to contribute to the success of the project. Step 2. Create energy model. Complete the energy model as early as possible. Create several iterations to determine the most cost-effective energy improvements while ensuring the project will exceed RE 90.1 2010 by at least 5%. See further explanation, creating a compliant 90.1 energy model. The whole building model must follow the USGBC's multifamily midrise simulation guidelines, which are based on ANSI/ASHRAE/ISNA Standard 90.1 2010, Appendix G, with errata. ASHRAE standards are not universally adopted around the world, and international projects may use an USGBC-approved equivalent standard. The 5% energy cost reduction does not include any reduction in purchased energy from renewable energy generation. The proposed design must be in compliance with all mandatory requirements of ANSI/ASHRAE/ISNA Standard 90.1 2010 and USGBC's multifamily midrise simulation guidelines. All assumptions must be documented and made available with the building model report. Submit the energy model reports and supporting calculations to USGBC for preliminary approval as early in the design process as possible. Step 3. Write air sealing and compartmentalization requirements. Include air sealing and compartmentalization details in construction documents and bid sheets. Qualified energy raters and green raters can help ensure that design details will ensure sufficient compartmentalization. Step 4. Complete pre-drywall inspection. After units have been sealed and insulated but before drywall is installed, the energy rater must perform the thermal enclosure inspection and compartmentalization inspection. Multifamily buildings may require additional pre-drywall inspections, depending on how fire barriers are installed. A blower door test is encouraged at this point to ensure that compartmentalization targets are met. A duct leakage test is encouraged to ensure that the distribution system is properly sealed. Insulation values and other items that affect energy performance should be compared with the energy model to ensure alignment. Step 5. Commission HVAC systems. A qualified energy rater must perform duct leakage testing for any in-unit ducted heating or cooling systems, if such tests were not performed earlier. The commissioning agent must verify the installation and performance of HVAC systems and provide a commissioning report. The commissioning agent prepares a current facilities requirements and operations and maintenance plan, which the building's facility management team should maintain. Step 6. Finalize energy model. The energy rater completes the energy model, confirming that it accurately reflects construction details in actual installation. The energy rater must verify all items on the multifamily midrise thermal enclosure inspection checklist. Submit the energy model to USGBC for final approval. Further explanation. Performance path. The performance path requires preparing an energy model, known as a HERS rating. The HERS rating uses a scale, or index, in which a home built to the specifications of the HERS reference home, based on the 2006 International Energy Conservation Code, achieves a score of 100, and a net zero energy home scores 0. The HERS index takes into account the size of building elements, window, floor, roof, and ceiling areas, and the characteristics of mechanical systems, lights, appliances, and insulation. The lower a home's HERS index, the more energy efficient it is compared with the HERS reference home. Each 1-point decrease in the HERS index corresponds to an estimated 1% reduction in energy consumption compared with the HERS reference home. Thus, a home with a HERS index of 75 is 25% more energy efficient than the HERS reference home. The Energy Star HERS index target varies based on the size of the home and the number of bedrooms. Energy Star requires that large homes with few bedrooms be designed and built to higher performance standards than smaller homes with more bedrooms. The HERS rating software provides the Energy Star HERS index target. Prescriptive path. The prescriptive path provides a single set of measures that can be used to construct an Energy Star certified home. Energy modeling is not required, however, no trade-offs are allowed. Under the performance path, a builder may upgrade certain facets of the home while installing other items at code minimum levels, effectively making trade-offs. The first step in the prescriptive path is to ensure eligibility by comparing the conditioned floor area, CFA, of the home to be built with the CFA of the benchmark home. If the CFA and number of bedrooms make the home eligible, build the home according to all requirements of the Energy Star reference design. Consult Energy Star for Homes, version 3, National Program Requirements, for eligibility guidelines. Further explanation. Creating a compliant 90.1 energy model. Step 1. Determine climate zone. Identify the project's climate zone according to ASHRAE 90.1 2010, Appendix B. See further explanation, Climate Zone Determination. Step 2. Review and address ASHRAE mandatory requirements. Early in the design process, review the mandatory provisions of ANSI/ASHRAE/ISNA Standard 90.1 2010, with ERRATA, or a USGBC approved equivalent standard for projects outside the U.S. Read through sections 5.4, 6.4, 7.4, 8.4, 9.4, and 10.4 to understand how the building design must respond to these requirements. Typically, the architect is responsible for section 5.4, building envelope. The mechanical engineer and plumbing designer are responsible for sections 6.4, HVAC, and 7.4, service water heating, and the electrical engineer is responsible for sections 8.4, power, and 9.4, lighting. Compliance with section 10.4 requires coordination across multiple disciplines. Ensure that the project complies with the mandatory measures throughout the design, construction, and commissioning process, particularly when major design decisions are implemented. Confirm that compliant components are included in the final construction documents. Step 3. Identify energy use target for building. Set an energy goal for the project early in the design process. Identifying an energy goal can help prioritize efficiency strategies, integrate systems, reduce first costs, and improve building performance. For EA credit annual energy use, the target must be established as energy use intensity, EUI, in kBTU per square foot year, kWh per square meter year, of source energy use. Consider using Energy Star's Target Finder to develop the EUI goal that will meet the credit requirements. More further explanation. Whole building energy simulation. Step 1. Review prerequisite and credit requirements. Thoroughly review the criteria and referenced standards for both EA prerequisite minimum energy performance and EA credit annual energy use before beginning the simulation. Buildings that meet the requirements for earning points under the credit, including mandatory requirements and excluding any credits from renewable energy, automatically achieve the prerequisite. Step 2. Identify Energy Modeler. Engage an Energy Modeler to perform the energy analysis. It is recommended that the qualifications of the Energy Modeler be carefully reviewed to ensure that the simulation will be performed accurately and according to the prerequisite requirements. Qualified energy modelers who have experience with numerous simulations for a variety of building types can help the design team interpret the results to develop an efficient building design. See further explanation, Energy Modeler Qualifications. Step 3. Develop Preliminary Energy Model. Consider creating preliminary energy models to analyze building design configuration and heating and cooling load reduction strategies. The preliminary models use information from the design to create a rough projection of energy usage in various scenarios. See further explanation, Developing a Preliminary Energy Model. A preliminary energy model is not required, however, developing an early model of the proposed design will help the design team explore the energy consequences of design options and will provide an early estimate of energy performance. When evaluating energy usage in different scenarios, consider strategies for lighting and daylighting, envelope, orientation, and passive conditioning and ventilating systems, in terms of projected energy savings and capital costs as they relate to all building systems. Step 4. Model potential HVAC system types. After building design configuration and load reduction strategies have been assessed and implemented, use the energy model to analyze the performance of HVAC system alternatives for the project. See further explanation, Modeling Potential _HVAC Systems. For best HVAC system performance, ensure that the system is properly sized. More effective system types, such as radiant heating and cooling or displacement ventilation, may be feasible when the loads are smaller, so begin the analysis by exploring ways to reduce the load. Step 5. Develop energy model for proposed design. Once the HVAC system and other design parameters are established, build or update the proposed building energy model to reflect the anticipated design. See further explanation, Building the proposed energy model. Update the proposed model to reflect changes that occur throughout the design process to optimize energy performance and assist with design decisions. Ensure that all efficiency strategies are analyzed well before design documents are finalized. Step 6. Create energy model for baseline design. Build a baseline model that reflects the minimum requirements according to ASHRAE 90.1 2010, Appendix G. See further explanation, Building the Baseline Energy Model. In addition, follow USGBC's Residential Energy Modeling Guidance, which defines how to create a baseline for residential spaces. When modifications are made to the proposed energy model, update the baseline accordingly. Consider constructing the baseline model early in the design process so that the design team can see the effect of design changes on the percentage savings relative to ASHRAE 90.1. This will contribute toward achieving more points under the related credit. Use the Energy Modeling Inputs and Quality Control Checklist spreadsheet, Appendix G, to help create the baseline model. This tool was designed to help project teams create a baseline model in alignment with Appendix G requirements. Step 7. Update baseline and proposed models based on final design. Update the proposed energy model to reflect final construction details and specifications and make any necessary corresponding updates to the baseline model. See further explanation, Finalizing the energy model. For elements or systems that cannot be readily modeled by the software, Use the exceptional calculation method or covenant modeling guidelines for unregulated loads. See further explanation, exceptional calculation method, and further explanation, common issues with energy modeling. Step 8. Determine energy cost savings. Compare the proposed model with the baseline model to determine the anticipated energy cost savings. See further explanation, energy cost savings. Ensure compliance with the prerequisite criteria for energy savings based on the building type, that is, new construction, major renovation, or core and shell. Energy costs offset by on-site renewable energy systems do not count toward energy savings for compliance with the prerequisite. Renewable energy may be included in the model for achievement of points under the related credit. Climate zone determination. Determining the right climate zone for the project is essential, since the requirements are specific to each climate zone. ASHRAE 90.1 2010 defines 8 climate zones. Miami is in Climate Zone 1, Anchorage is in Climate Zone 8, and 3 climate types, A, moist, B, dry, and C, marine. To find the project's climate zone and type, consult ASHRAE 90.1 2010, Appendix B, for the appropriate state and county. If the project's county is not listed, use the climate zone listed for the state as a whole. For projects outside the U.S., see further explanation, international tips. Energy Modeler Qualifications. The energy modeler should have the following competences: a comprehensive understanding of all the building systems related to energy performance and the information needed to construct a model using the selected software. The ability to understand and explain capabilities and limitations of modeling software in regards to the strategies the team would like to pursue. Awareness of how much time the design team needs to provide information, feedback, and responses to the modeling exercise. Experience with design phase modeling. The ability to demonstrate how energy modeling can be used to perform cost-benefit analysis. Experience in modeling projects using ASHRAE 90.1, Appendix G, Performance Rating Method, or a thorough understanding of this approach. Experience in modeling multifamily projects following USGBC's Residential Energy Modeling Guidance, EPA's Energy Star High-Rises Simulation Guidelines, or a thorough understanding of these protocols. The ability to perform quality control to ensure that the modeling inputs accurately reflect the proposed design and Appendix G baseline. The ability to evaluate the simulation results for reasonableness in relation to the energy modeling inputs, including energy consumption by end use, cost, and the performance savings claimed. The ability to validate the model through review of the actual utility bills during the occupancy phase. Developing a preliminary energy model. Although not required for this prerequisite, preparation of a preliminary model can facilitate achievement of the related credit, which requires analysis of efficiency measures. Past analyses of similar buildings or published data, such as the AEDGs, may also be used to guide decision-making, though the results will be less project-specific. A preliminary model includes design elements identified during schematic design and design development and generates a preliminary estimate of energy consumption and an end-use profile. Evaluate how changes to the following elements affect HVAC sizing, energy consumption, lighting, renewable energy opportunities, and other aspects of energy performance. Program and operations, multifunctioning spaces, operating schedules, space allotment per person, teleworking, reduction of building area, operations and maintenance. Site conditions, shading, exterior lighting, hardscape, landscaping, adjacent site conditions. Massing and orientation. Envelope, insulation values, window-to-wall ratios, glazing characteristics, shading, and window operability. Lighting levels and interior surface reflectance. Thermal comfort range options. Passive conditioning and natural ventilation strategies. When examining alternative strategies, also consider the effect on human performance. For example, increasing daylighting may cause glare. Typical steps in preliminary energy modeling are as follows. 1. Gather information about building loads and systems. Investigate case studies of similar building in similar climates and contact local utilities for energy rates and demand charges. Determine applicable building energy codes, including any local variations. For existing buildings, review drawings, specifications, operations and maintenance manuals, commissioning reports, energy audit reports, and utility bills. The AEDGs may provide useful information regarding design practices specific to building types and climate zones. 2. Engage the design team early to investigate opportunities for load reduction. Coordinate with the architect to identify options for envelope insulation values, building orientation, and shading, variables that can affect load, especially on externally load-dominated buildings. Some strategies, such as building massing and orientation, are most effectively evaluated during the concept phase of design, before the preliminary energy model, and is not required for this prerequisite. 3. Analyze several design alternatives to investigate the combined load reduction potential of multiple strategies. How strategies alter energy consumption varies by building type and climate zone. Examine energy use by end use and heating and cooling load distribution to identify effective load reduction and energy efficiency opportunities. 4. Investigate interconnected strategies. The additional costs of high-performance envelope elements may be offset by smaller, less costly HVAC systems. For example, energy modeling could evaluate the effect of a fenestration and shading configuration, with daylight harvesting controls, on cooling, heating and fan loads, HVAC system capacities, and total building energy consumption and cost. A lifecycle cost analysis for this scenario would indicate the net increase or decrease in capital costs and the potential savings over multiple years. When evaluating the capital cost, consider trade-offs between the higher capital cost for the shading and daylight harvesting controls and the lower capital costs for a smaller HVAC system. 5. Use the model to compare potential performance with the project's energy goals. Modeling HVAC systems. Although not required for this prerequisite, an evaluation of HVAC system alternatives can help the design team optimize energy consumption. The modeler should analyze the performance of several efficient HVAC systems to understand the potential energy savings associated with each one. This information enables the design team to compare lifecycle costs, rather than just first costs. The lifecycle cost analysis should follow the analysis of load reductions, which may affect the lifecycle cost. The chosen HVAC system can then be further optimized through additional energy modeling that analyzes the potential efficiency gains of the system components and/or assigns different systems to different zones. Typical steps for HVAC system type modeling include the following. 1. Coordinate with the mechanical engineer, since decreased loads may affect mechanical system sizing or potential system types. Compare high-efficiency HVAC systems with typical systems for reductions in operating costs, energy, maintenance. Weigh this against the higher first costs of more efficient equipment. Evaluate the potential for reducing the first cost of HVAC equipment by reducing the loads. Include not only the smaller equipment but also the infrastructure related to HVAC, ductwork, piping, controls, and in some cases, building volume or floor area for these components. 2. For the selected system, analyze and optimize additional HVAC energy efficiency measures, including equipment efficiency, energy recovery, economizers, and demand-controlled ventilation. 3. Coordinate with the architect and structural engineer, since different system types may influence space, height, or structural requirements. For example, underfloor air conditioning may influence the exterior envelope design and could increase or decrease the height of the building. Building the proposed energy model. An energy model of the proposed design is required for prerequisite compliance under Option 1. A team that has already prepared a preliminary model may update it to reflect the newest design information throughout the project. Create or update proposed building characteristics based on the latest information and specifications on systems, assemblies, and equipment in the current design. This can be accomplished as early as design development to estimate projected savings, and later updated when the construction documents are complete. Then analyze remaining efficiency strategies that the team would like to consider before the design documents are finalized. For example, the proposed energy model could be used to evaluate the performance and cost implications of value engineering decisions. Building the baseline energy model. Developing a baseline energy model is a detailed process that requires a good working knowledge of ASHRAE 90.1 2010, Appendix G, and familiarity with the relevant sections of the standard. In addition, energy modelers should be well versed in USGBC's residential energy modeling guidance. The baseline model represents a typical design for a building of the same size and use as the proposed building. It meets but does not exceed the performance requirements of ASHRAE 90.1 2010 and is used as a comparison to calculate the percentage energy cost savings for the project design. In general, baseline development begins by changing the inputs for all the components, assemblies, and systems of the proposed design energy model to minimally compliant input values. In accordance with 90.1 to 2010 Appendix G, determine or update baseline values for each system, assembly, and piece of equipment for the appropriate climate zone, building type, and fuel types. If the energy simulation software automates some or all the baseline generation, review the automated baseline model inputs against the expected baseline values and confirm consistency. See further explanation, Common issues with energy modeling. Preparation of the initial baseline model is best undertaken during the design development phase, after major design decisions have been made, so that modeling can evaluate whether the project is likely to meet energy savings targets, or achieve points under the related credit. The baseline model will typically need to be updated based on the final project design. Finalizing the energy models. Update the proposed model based on the information and specifications for systems, assemblies, and equipment in the final construction documents. Confirm that all efficiency measures claimed have been incorporated into the design. Include all energy consumption and costs within and associated with the building project. Ensure that assumptions used in earlier versions of the model are replaced with actual data from the construction documents. For example, if proposed chiller control sequences were assumed in the preliminary model, use the actual control sequences from the construction documents for the final version. Update the baseline model as necessary based on the project's final construction documents, including changes in occupant density, required outdoor airflow, thermostat set points, and system or fuel types. The model will have to be updated again if any changes during construction affect efficiency measures. Schedules must be modeled correctly for both the proposed and baseline models. See further explanation, schedules. Perform a quality control check to verify that all Appendix G and LEED modeling guidelines have been followed. Record both the proposed and baseline values in the Appendix G energy modeling inputs and quality control checklist spreadsheet. This record of energy conservation measures is a good tool for confirming that proposed building characteristics and baseline values have been selected properly. Document the input assumptions for receptacle and process loads. These loads should be modeled accurately to reflect the actual expected energy consumption of the building. Per ASHRAE 90.1 2010, Table G 3.112, receptacle and process loads must be modeled identically in both the proposed and baseline models, unless there are specific efficiency requirements listed in sections 5 through 10 or the residential energy modeling guidance that allow a less stringent baseline requirement, for example, motor efficiency. If the project claims savings for variations in power requirements, schedules, or control sequences, the burden of proof is on the project team to document that the design represents a significant departure from conventional practice. If an energy efficiency measure cannot be explicitly modeled, the team may use Section G2.5, Exceptional Calculation Method. See further explanation, Exceptional Calculation Method. Verify the final energy cost savings. Evaluate the energy savings by end use for reasonableness based on the differences in the modeling inputs between the baseline and proposed models. See further explanation, Energy Cost Savings. Use Figure 1 to help verify proposed energy savings. Figure 1. Steps to verify proposed energy savings. Project and content. Inputs. Outputs. End-use consistency. Building level consistency. Special outputs. Schedules. For optimal results, ensure that the schedule inputs into the model accurately reflect the project building's operation. If anticipated operating schedules are unknown, helpful guidance for determining model inputs for occupancy, lighting, HVAC system, receptacle power, and service hot water consumption values can be found in the ASHRAE 90.1 2010 User's Manual, Appendix G and USGBC's Residential Energy Modeling Guidance. Schedules must be identical in both the baseline and the proposed cases unless documented in an exceptional calculation or specifically allowed by ASHRAE 90.1 2010 Appendix G. See further explanation, Exceptional Calculation Method, or USGBC's Residential Energy Modeling Guidance. Certain space types may require specific schedules based on anticipated operation and may vary by space type. For example, a server room may have different temperature schedules than an occupied space. Exceptions to Section G3.1. First of may require modeling of a different baseline HVAC system type in spaces with schedules that vary significantly from the rest of the building. Different lighting schedules may be used for a project with both office and retail occupancy when the space-by-space method is used or when the building area method is used with multiple building type classifications. Different schedules cannot be used, however, if an average lighting power density is applied to the whole project. Ventilation and infiltration schedules should also be adjusted to ensure the same amount of outside air delivery and infiltration between baseline and proposed cases, except for specific exceptions allowed by Appendix G. Thank you for watching. We will continue this credit to the next video. Due to its long presentation. Watch for the next video. LEED V4 Homes, Energy and Atmosphere Prerequisite 1. Minimum Energy Performance Part 2. If you wish to get the PDF or PowerPoint copy of this presentation for free, please click the link below or email me at nelca_roco@yahoo.com.